Hello everyone, welcome to online session of electromagnetic waves, and today's session I am going to discuss about the following topics: electromagnetic spectrum and electromagnetic waves, the plane electromagnetic waves, equation in terms of electric field using Maxwell's equation, transverse nature of electromagnetic waves, polarization of plane wave, and some numericals related to the topic. So before going to the electromagnetic waves, let us see what is the electromagnetic spectrum. An electromagnetic spectrum is the range of all possible frequencies of electromagnetic radiation. This spectrum extends from below the low frequencies used for the radio communications to the gamma radiations at the short wavelength region. And we can see in the slide the range in which the different type of radiations covered in the electromagnetic spectrum. It starts with the radio waves. The frequency of these radio waves is 10^4 Hertz, and next it is microwaves. Frequency is 10^8 Hertz. Infrared radiations 10^12 Hertz, and visible region. This is one of the smallest segment in the electromagnetic spectrum. It covers 7 different colors with joy. The frequency range of visible radiation is 10^14 to 15 Hertz. Then comes the ultraviolet radiations. The frequency is 10^16 Hertz. Then X-rays 10^18 Hertz, and gamma radiations are 10^20 Hertz. So this is the radiations which are covered in the electromagnetic spectrum. Now, the most of the electromagnetic spectrum is used for spectroscopic and other probing interactions. Also, these radiations are used in communication and manufacturing technology. So, let us see what are electromagnetic waves. Actually, the waves associated with the electromagnetic spectrum or the electromagnetic radiations are called electromagnetic waves. These waves are transverse in nature. The transverse in the sense their direction of propagation in a direction perpendicular to the propagation. That is what the transverse nature of the electromagnetic radiations. Then in general we say the electromagnetic waves are the waves that are created as a vibrations between the electric field and magnetic field. So which means electromagnetic waves consist of electric vector and magnetic vectors. Generally these magnetic vector and electric vector, they are mutually perpendicular to each other when an electromagnetic wave generating or propagating in a particular direction in a given medium. So electromagnetic waves are composed of oscillating magnetic and electric vectors. In fact, we say it is electromagnetic waves which are composed of oscillating magnetic and electric vectors. An electromagnetic wave comprises of varying electric and magnetic fields in a direction perpendicular to the direction of propagation, which is shown in the figure. The variation in the electric field and the magnetic fields, that is E and B. E is the electric field vector and B is the magnetic field vector along X and Y axis respectively. But the direction of propagation is shown along Z directions. So which means electric vector is in one direction, magnetic vector is in the direction perpendicular to it, and entire electromagnetic wave which is propagating in the other direction, Z direction, which means perpendicular to these two vectors. In turn, the electromagnetic wave is traveling in a direction perpendicular to the E and B vector. The field strength of variation of either of them is the pattern of wave, and each of these vector has a wavelength. The electric and magnetic waves always appear together as a collective entity as called electromagnetic wave. So I hope it's clear. So electromagnetic wave in the sense the electric vector as well as the magnetic vector, they are mutually perpendicular to each other. In other words, they are oscillating perpendicular to each other. As a collectively these two vectors traveling in a particular direction, and that direction is perpendicular to the electric and magnetic vectors. Such an wave is called electromagnetic wave. Next concept is the plane electromagnetic wave, or we say plane waves. The plane electromagnetic waves are the waves that possesses variations only in the direction of propagation, and their characteristics remain constant across the planes. So plane waves are the waves that possesses variations only in the direction of propagation, and their characteristics remains constant across the planes. Planes in the sense normally normal to the direction of propagation. Across the planes in the sense normal to the direction of propagation. So in a plane electromagnetic wave, electric and magnetic fields are uniform over a plane perpendicular to the direction of propagation. So say for instance, electromagnetic waves propagating along a certain axis, say x-axis or y or z, anything you can take, then we call such waves are uniform plane waves, in which electric field is independent of y and z axis, which means if the electromagnetic wave is propagating in the x direction, in which the electric field is independent of y and z axis, but it is a function of x and time only. X in the sense the position coordinate and time in the time coordinate. So the variation in the electric and magnetic vector as a electromagnetic wave, when it is propagating in a direction, it functions with respect to position as well as the time. So when a uniform plane waves are propagating in a medium along the x direction, there will be no field component along the direction of propagation. There will be no components along the direction of propagation. So which means components, say dou by dou y of hy is equal to dou by dou y of hz, that's equal to dou by dou z of hz, that is equal to dou by dou z of hz, that is equal to 0. So meaning is the component along x direction, y direction, y component as well as the z component is 0. That means there is no existence of the component along y and z direction. That is the meaning. That's the meaning of that particular equation. Now to write the equations for plane electromagnetic waves in vacuum, that's for vector E and vector B, let us consider a plane electromagnetic wave of wavelength lambda, which is propagating in a vacuum along the positive x direction. Now the electric field associated with this wave may be parallel to the y directions, that is vector E. The picture I have shown in the first slide, and I am continuing the discussion. And there is a magnetic field associated with the wave which is oriented parallel to the z directions. It is denoted as vector Bz. So in this case, let me write the expression for the electric vector, that is vector Ey, that's shown in the slide. is equal to A cos open bracket 2 pi by lambda, again open bracket, x minus ct close bracket, and ay cap is the unit vector there. So that is the electric vector component of the electromagnetic wave. And similarly, the magnetic vector component, that is Bz, is equal to minus 1 by c A cos of open bracket 2 pi by lambda open bracket x minus ct close bracket az cap. So these are the just two expressions that represents the electric vector and magnetic vector, where c is the velocity of propagation of the electromagnetic wave in vacuum, and x is the, obviously that will be the position coordinate, and t is a time coordinate, and lambda is the wavelength, and a is the amplitude of vibration of electric as well as the magnetic fields. So here the vector Ey and vector Bz are mutually perpendicular to electromagnetic waves. So that's quite obvious when an electromagnetic which is propagating in a given medium wherein electric and magnetic fields are perpendicular to each other, and also these E vector and B vector perpendicular to the direction of propagations. That is what the propagation of electromagnetic wave. So in classical wave, we have a equation for classical wave for an oscillating physical entity, that is gradient square of f minus 1 by v square into dou square f by dou x square is equal to 0. That's a classical wave equation for an oscillating physical entity. That is required for the later discussions. That's why I mentioned it. And you know, once we say the classical wave equation, the wave which represents for a macromolecules. It's not a micromolecule, for macromolecules. So let us take the next concept, that is derivation of wave equation in terms of electric field using Maxwell's equation. To derive these expressions, let us consider the Maxwell's equation. That means Maxwell's third and fourth equation. The fourth equation is, that is a curl of a vector h is equal to vector j plus dou by dou t of vector d. That's nothing but Ampere's Maxwell law as well. And the third equation, that is a curl of a vector E is equal to minus dou by dou t of vector B. So call this equation as equation number 1 and 2 as I have shown in the slide. So we have the expression for electric flux density, that is D equal to epsilon E into vector E. Now we can substitute this value of vector D in the equation number 1, so that curl H can be written as vector J plus epsilon into dou by dou t of vector E. This is the equation number 3. Also, the relationship between the magnetic field and magnetic flux, that is B equal to mu H, where mu is the permeability of the medium, and substitute this B equal to mu H in equation number 2. So curl of a vector E is equal to minus mu into dou by dou t of vector H. Let me call this as equation number 4. The electric field equation relating the spatial coordinates of vector E to its time coordinate. So that can be written by taking the curl of both sides of the equation number 4. So that means equation number 4 is a curl of vector E is equal to minus of mu into dou by dou t of vector H. Now let us take the curl of it. It is a curl of a curl E is equal to minus dou by dou t of curl H. I am applying the curl application on the equation number 4. So the equation represents the equation number 5 now. That's a curl of vector E is equal to minus mu into dou by dou t of curl of H. But we have a vector identities. So vector identity analogy we have discussed in one of the previous class. So wherein I have written the same equation, I am using that equation again, that is curl of vector E is equal to gradient of divergence of vector E minus gradient square vector E. So this is the one equation written using vector identities. So please remember this, that is a curl of vector E is equal to gradient of divergence of vector E minus gradient square vector E. Now since divergence of vector E is equal to rho v by epsilon, that means where rho v is the volume charge density. So this can be written as divergence of, in fact this can be written as the gradient of rho v by epsilon minus gradient square vector E, which means now we call this as equation number 6. Using equation number 5 and 6, we have a gradient of rho v by epsilon minus gradient square vector E is equal to minus mu into dou by dou t of curl of vector H. That is by using equation number 5 and 6. We have taken the right hand side of these two expressions and equated, and I got this expression. Now next step is the gradient of rho v by epsilon minus gradient square of vector E is equal to minus of mu into dou by dou t of open bracket j plus dou by dou t of vector D. So here I have written the expression for curl of a vector H. We know that curl of a vector H is equal to j plus dou by dou t of vector D. So the same thing I have written. Further I simplified, where dou by dou t of vector D is written as dou by dou t of epsilon E. Therefore epsilon is taken outside. Therefore epsilon into dou by dou t of vector E. Therefore that particular part of the equation is gradient of rho v by epsilon minus gradient square vector E is equal to minus dou by dou t of open bracket vector j plus epsilon into dou by dou t of vector E. That means the gradient square of vector E is vector E minus mu epsilon dou square E by dou t square is equal to mu into dou by dou t of vector j plus gradient of rho v by epsilon. That is by rearranging. I am collecting that E vector E terms. That's why the rearrangement is done one side. On the other side I am collecting the mu terms. That means j and rho v terms, the current related term. So we got the equation number 7 there. Now for free charges, the rho v is 0, that is volume charge density is 0. So in other words, the current density. So if there is no charges, obviously current is not there. So current density is 0. Therefore the gradient square of vector E minus mu epsilon into dou square vector E by dou t square is equal to 0. This is the equation number 8. So similar way we can write the expression for magnetic field. Actually the equation number 8 represents the wave equation in terms of the electric field. So similar way we can write the equation in terms of magnetic fields by similar procedures. Therefore that equation is the gradient square H minus mu epsilon dou square by dou t square of vector H, that is equal to 0. Call this is equation number 9. Now next step is we have a equation number 8 and 9. So this equation number 8 and 9 that represents the wave equation in terms of the electric field and magnetic field respectively, compare these two expressions with the classical wave equations that I have shown in the previous slide. So that is gradient square of f minus 1 by v square dou square by dou t square of vector f is equal to 0. So call this equation number 10. Now by comparing these three expressions, I can write the 1 by v square is equal to mu epsilon. So that means you can see there first term is gradient square E, here the gradient square F. So that's a classical wave equation, but here it is, we have a quantum ideas. So when you compare this, what happens is the right hand side, second term where we have a 1 by v square in the equation number 10, and the equation number 8 we have a mu epsilon. So other terms are common. That's why we got that 1 by v square is equal to mu epsilon. In other words, v is equal to 1 by square root of mu epsilon. So this is the expression for velocity. So also mu equal to mu r into mu naught. Similarly, epsilon equal to epsilon r into epsilon naught. So this is the relation between the relative permeability, that's mu r, and the permeability of the medium and the permeability of the free space, that is mu naught. This is how mu equal to mu r into mu naught. That will be the equation for the permeability, and the second term is for epsilon is equal to epsilon naught into epsilon r. So by using this, you can write the expression for C, that is speed of the electromagnetic waves in vacuum, that is C equal to 1 by square root of mu naught epsilon naught. And you know what is mu naught and epsilon naught. Mu naught is the permeability of the free space, and epsilon naught is the permittivity of the free space. The relation between electric vector and magnetic vector for a uniform plane wave. The equation for a plane electromagnetic wave in terms of the electric field vector E and magnetic field vector B is given by E by B is equal to square root of mu by epsilon. And already I have discussed the relation between mu and mu r. Similarly, epsilon and epsilon r, it is shown in this slide. For vacuum, the ratio of the electric vector and magnetic vector, it is given by square root of mu naught by epsilon naught. Next topic is the transverse nature of electromagnetic wave. Please remember the above expression, that is for the ratio of the electric vector to the magnetic vector. So from that you can determine the permeability of the medium or the permittivity of the medium. That can be evaluated using that, along with the equations of mu equal to mu r into mu naught, and also epsilon is equal to epsilon r into epsilon naught. Next topic is the transverse nature of electromagnetic waves. Consider a uniform plane wave propagating along x direction in a given medium where there are no free charges. So from the Maxwell's equation, that's a first equation, that divergence of a vector D is equal to rho. Now divergence of D is nothing but epsilon vector E, that I have substituted D is equal to epsilon vector E, that is equal to rho, that's equal to 0 for a free space. Therefore, in case of free space, we can write the expression for electric vector, that's in 3 dimension, that's dou by dou x of Ex plus dou by dou y of Ey and plus dou by dou z of Ez, that is equal to 0. That's for free space, the electric vectors in 3 dimension, that is equal to 0, right. In this case, as the wave propagating along x direction, think of the wave is propagating along x direction, the Ey and Ez components remain constant along y and z directions respectively. Which means the derivative of these components, that means dou by dou y of Ey, that is equal to 0. Also dou by dou z of Ez, that is also 0. Why? Because they remains constant when the wave is propagating along x direction. So since it is constant, the derivative of that component is 0. Therefore, from the expression 1, that what we call the dou by dou x of Ex plus dou by dou y of Ey plus dou by dou z of Ez equal to 0, which is called as equation number 1, as shown in this slide, right? Now we got the two terms in the expression as 0. Therefore, we also got dou by dou x of Ex is equal to 0. So for a plane wave, Ex cannot be a constant as it is a periodic. When it is propagating in a particular direction, the wave propagation is in terms of the periodic manner. Therefore, for any plane waves, the x component of the electric vector is not a constant as it is a periodic one. Therefore, Ex is equal to 0. Therefore, Ex equal to 0. Ex equal to 0 means a uniform plane wave propagating in a x direction has no x component of the electric field. It indicates that the electric field is perpendicular to the direction of propagation. That's the meaning. So if Ex equal to 0, which means a uniform plane wave propagating in the x direction which has no x component of electric field. That means it shows that the electric field is perpendicular to the direction of propagation. Similarly, or similar analysis that can be shown, the x component of magnetic field is also 0. Next topic is the polarization of a plane wave, and we know what are plane waves. Let us go for the polarization of plane waves. When we think about polarization, we consider only the electric field variation of electromagnetic wave, assuming that the associated magnetic field variation is invariable in the perpendicular plane. The reason for choosing the electric vector over the magnetic vector, because the electric vector is predominantly effective at exerting forces or doing some work on charges. That's in comparison to that of vector B. So that's why we prefer the electric vector when we are discussing about the polarization of a plane wave. So why? Because the electric vector is predominantly effective at exerting forces or doing some work on the charges. Thus, the electric field is taken as the representative field for a wave from the particular point M that is shown in the figure. So that's a starting point in the figure, you can see there. Now one consider the variation of E with the distance, E in the sense the electric vector. One consider the variation of electric vector E with the distance along Z axis, and the variation is shown in the same figure. We see that the variation of electric vector E increases from 0, reaches a maximum, and gradually becomes 0 at another point N, that you can see in this slide. Then starts increasing in the positive direction to reach a maximum, following which it can becomes 0 again. Just for an observation on the variation of electric vector E from a location to which the path of propagation of the wave is directed, the tip of the electric vector appears to oscillating along a single straight line as shown in the figure. The separate single line is shown in the slide. So that EE, that represents the electric vector, single line. So the point is, just for an observation, the variation of the electric vector E from a location to which the path of propagation of the wave is directed, that tip of the electric vector which appears to oscillating along a single straight line which is shown in the figure, right. Thus, the polarization of a uniform plane wave refers to the time varying behavior of electric field at some point in space. So, polarization of a uniform plane wave refers to the time varying behavior of the electric field at some point in space. Now, there are different type of polarized waves, in other words, the polarization. So, namely the linear polarization, circular polarization and elliptical polarization. So, let us take up the linear polarization topic. In a linearly polarized electromagnetic wave, the electric vector remains in one directional. To understand this concept, let us take an example. Consider a wave which is propagating along z direction. The electric field can have a x and y component. So it's very clear. The electromagnetic wave which is propagating along z directions, the electric field can have x and y component, and remember, x and y components are mutually perpendicular to each other. Now these components are referred as Ex and Ey, that is shown in the slide. The resultant electric vector will be oriented in a particular direction such that the theta, that is tan theta, is equal to Ex by Ey. As wave progresses, the x component and y component of the electric vector changes in magnitude, but the change is always constant. That means the ratio of Ey by Ex remains constant. So please remember, here the component Ex and Ey will change in magnitude, but ratio of the change, that is Ey by Ex, that will remains constant. The electric vector varies from 0 to E maximum and back to 0 in one direction, and then 0 to E maximum and back to 0 in the opposite directions. The electric vector appears to a straight line as shown in the figure. That is how things are happening in the linearly polarized electromagnetic waves. Next, the electric intensity of a uniform plane wave in a conducting medium can be written as, for a linearly polarized wave, it is the vector E of z comma t. That means the electric vector, expression for electric vector when it is propagating along z direction and in a time coordinate. Z is the position coordinate of that vector that is propagating along z direction, and t is the time coordinate. Therefore, E of z comma t, that can be written as E naught, that represents the amplitude of the electric vector, the electromagnetic wave, and e power minus alpha z cos of open bracket omega t minus bz close bracket az cap. So this is the equation which represents linearly polarized wave as the electromagnetic field always in the z direction. So this is the equation which represents linear polarized wave as the electric field is in z directions. Now this equation has two components, that is Ex of z comma t and Ey of z comma t. These are the two components. So let us see what are the expressions for Ex of z comma t and Ey of z comma t. So Ex of z comma t can be written as E naught of x, that is E naught x e power minus alpha z open bracket its cos open bracket omega t minus beta z plus theta x, and Ey component of z comma t, that is Ey of z comma t is equal to E naught of y e power minus alpha z cos of omega open bracket omega t minus beta z plus theta y. So these are the two components which I have taken from the original expressions, which represents the linearly polarized wave equation for an electromagnetic wave. Now let us put some condition saying that z is equal to 0. Component z is 0 when Ex and Ey are in phase. Then theta x is equal to theta y, which means the component Ex and Ey, they are in phase. There is no out of phase or phase difference. So therefore the theta x is equal to theta y. So we simply call it as theta, and z is 0. With this condition, let us substitute this condition in the expressions. So therefore Ex of 0 comma t is equal to, why, because the z is 0, therefore Ex of 0 comma t is equal to E0 of x e power minus alpha z cos of open bracket omega t minus beta z plus theta. I will call this is equation number 1, and Ey of 0 comma t is equal to E0 y e power minus alpha z cos of open bracket omega t minus beta z plus theta. Let me call it as equation number 2. And in these expressions, beta is the phase constant and z is the direction in which electromagnetic wave is propagating, and omega is the angular frequency, t is the time coordinate. Okay. Now we have got two expressions, equation number 1 and equation number 2. Dividing equation number 1 by 2, that will yield E of x 0 comma t vector Ex of 0 comma t is equal to E0x by E0y. That means the E0 x component, E0 y component into Ey of 0 comma t. This equation is written by dividing equation number 1 by equation number 2. So equation describes a linear relationship between the two components, that is Ex and Ey component. Therefore the electromagnetic wave is linearly polarized. So one topic is proved, linear polarization of electromagnetic wave. Why? Because this equation represents the linear relationship between two components, that is Ex and Ey component. Therefore the plane wave is linearly polarized. Next topic is the circular polarization. Here in the case of circular polarization, the electric vector describes a circle over one cycle as the plane wave advances. The phase difference existing between the two components Ex and Ey, that will be out of phase by 90 degrees. Please remember, in the previous case there is no phase difference in the linearly polarized cases, but when it comes to the circular polarization there is a phase difference existing between the two components, that is Ex and Ey. Therefore, you can see the picture. The phase difference existing between the Ex and Ey is 90 degrees. The electric vector will have a constant magnitude but changes its directions, describing a circle. Now here in this case, the electric vector will have a constant magnitude but changes its directions, describing a circle. That is the difference between the linear polarization and circular polarization. There the ratio of these two components, magnitude, will be constant. Similarly, similar to the previous discussions, we came across the wave propagation along z directions. Therefore, the same equations which we have used for the linear polarization case, same thing will be adopted here as well. And I am straight away writing the component of E of z comma t in the case of circular polarization. That is, Ex of z comma t is equal to E naught x e power minus alpha z cos of open bracket omega t minus beta z plus theta x, and Ey of z comma t is equal to E naught y e power minus alpha z cos of open bracket omega t minus beta z plus theta y. So these are the two components of the electric vector, Ex and Ey components. When the electromagnetic wave which is propagating in the z directions, we had our original expression. From that, the component of that electric vector, Ex and Ey component, is written separately. Now let us put the condition under the case of circular polarized wave. Here the theta x is equal to theta y plus or minus 90 degrees and z is equal to 0 when E0x, that is E naught x, is equal to E naught y, that's equal to E naught. As I mentioned, the amplitudes along x and y component of the electric vector, it is equal. Therefore, simply I will write, instead of E0x and E0y, let me write it is E naught. So E naught, I am substituting z is 0, right? So equation becomes Ex of 0 comma t, that's equal to E naught into e power minus alpha into 0 sine of open bracket omega t minus beta z plus theta y. Why? Because that is cos of 90 plus theta, that will be written as sine theta. Therefore, sine of omega t minus beta z plus theta y. I will call this is equation number 1. Next, second thing is, second component in fact, that is vector Ey of 0 comma t is equal to E naught e power minus alpha 0 cos of open bracket omega t minus beta z plus theta y close bracket. Call this is equation number 2. Now these are the two equation represents x component and y component after implementing the conditions. Now again squaring and adding of the equation number 1 and 2. So that will gives rise to the left sides, that's e square x of 0 comma t plus e square y of 0 comma t, that is equal to E naught square only. Why? Because the sine square theta plus cos square theta is equal to 1. With that equations, the other terms in the right hand side will be 1. And also e power 0 is 1 there. That's why we got only E naught square. So this equation represents or describes the circle. Therefore, the plane electromagnetic waves are circularly polarized. So why? Because that equation is the equation of circle. That's why we say the electromagnetic waves are circularly polarized. Next topic is the elliptical polarization. So in the case of the elliptical polarization, A polarized plane wave of electric vector E constantly changes, but its magnitude and direction, and the electric vector describes the ellipse during the one cycle. So here it is, the elliptical polarized plane wave, the electric vector E constantly changes. That means the magnitude of the electric vector is constantly changes, both in magnitude as well as the direction. Therefore, the electric vector describes a ellipse. In an elliptically polarized wave, there will be a phase difference between Ex and Ey, and that phase difference is not equal to 90 degree as in the case of circularly polarized electromagnetic waves. So when the components are out of phase, the electric vector E rotates as a function of time, describing an ellipse. So it attains the maximum value E maximum in the direction of the major axis and a minimum value E minimum in the direction of minor axis. That you can see in the picture. Maximum and minimum values, how it is going to trace when it will form a elliptical form. Now when this form a elliptical direction, the elliptical geometry, then the expression for the electromagnetic wave in terms of electric vector, which is similar to the equation which we have used for the linear polarization. Therefore, I will again go for the component of that electric vector, that is E of z comma t, as two components, that is Ex of z comma t. So what is the meaning of E of z comma t? That is a electromagnetic wave which is propagating along z directions with respect to time. That is what exactly the E of z comma t. Now this E of z comma t has two components. That means the electric vector of that electromagnetic wave has got two components, that is Ex of z comma t and Ey of z comma t. So that is given as or that can be written as Ex of z comma t is equal to E naught of x e power minus alpha z cos of open bracket omega t minus beta z plus theta x close bracket. Also the other component Ey of z comma t is equal to E naught y e power minus alpha z cos of open bracket omega t minus beta z plus theta y close bracket. Now let us put the condition in the case of elliptical polarizations, as we have discussed previously about the condition of the elliptical polarization. So here the E naught x is not equal to E naught y. That means the magnitude of the electric vector along x component and y component are not equal. I have already explained. So I am writing in terms of equations, that is E naught x is not equal to E naught y, and z is equal to 0. Z is equal to 0. Then there is a phase difference existing between that, that is theta y is equal to theta x plus or minus 90 degrees. Alright, now let me apply these conditions in the above equations. Therefore, equation can be rewritten as, so Ex of 0 comma t is equal to E naught of x into cos of open bracket omega t minus beta z plus theta x. That will be the equation. In turn, I can write I have taken that E naught to the numerator, in the denominator in fact, yeah. That is therefore the Ex of 0 comma t divided by E naught x is equal to cos of omega t minus beta z plus theta x. Call this is equation number 1. And one more part is, that is Ey of 0 comma t divided by E naught y is equal to, now sine of, it is not cos because I am applying the condition where theta y is equal to theta x plus or minus 90 degree. Therefore, cos of that 90 plus theta, that can be written as sin theta. Therefore, sin of omega t minus beta z plus theta x. So, same procedure I have implemented here also, that E naught y, that's in the right side, that is taken to the left side, that will be dividing conditions. Okay, let me call this as equation number 2. Now from the equation number 1 and 2, again squaring and adding equation number 1 and 2. So it will yield, it's quite obvious, if you square and add, what happens, that E naught x and E naught y, that will be remains. Therefore E x of 0 comma t divided by E naught x whole square plus E y of 0 comma t divided by E naught y whole square is equal to 1. Why? Because cos square theta plus sin square theta, that is 1. So this is the equation which represents for ellipse. Therefore the given electromagnetic wave is elliptically polarized. So I have explained about the circularly polarized electromagnetic wave, elliptically polarized wave and linearly polarized electromagnetic wave. So I hope you have got the difference between the three different type of polarizations. So what way the theta value is changing. In the first conditions, there is theta x and theta y, they are equal, and the second case there is a phase difference existing between theta x and theta y, and the third case, that is elliptical polarization, again the theta x and theta are existing, that means phase difference is existing between the Ex and Ey component, and magnitudes of the Ex and Ey component, that will be same in the first case, and second there is again it is same, but in the third case Ex and Ey, they are not equal. That is how three different type of polarizations I have discussed by taking these conditions. Next we will move on to the numericals. A circular loop of 10 centimeter radius is located in the xy plane in a magnetic field given by vector B is equal to 0.5 cos open bracket 377t close bracket, again open bracket 3ay plus 4az cap close bracket, t means Tesla, that is the unit of magnetic field there. Determine the voltage induced in the loop. So this is the problem related to the Faraday law of electromagnetic induction. So the circular loop is given, the radius of that loop is given, which is located in the xy plane in a magnetic field. That's what they given, and also the expression for magnetic field is given. Now once radius is given, you can write radius is equal to 10 centimeter or 0.1 meters in SI units. So once if you have a radius data, you can evaluate the area of that loop, that's 5r square. So we got 3.14 into 0.1 whole square. So circular loop located in xy plane, so unit normal to the plane along the z direction, that means az cap. So that's very, very important, we need to find out. So once the loop is located in xy plane, their unit normal is perpendicular to that, therefore z directions, therefore direction represents az cap. Therefore the unit area is a vector entity, ds vector is equal to ds into that unit normal az cap. Alright, the given that vector b is equal to 0.5 cos of open bracket 377t close bracket, again open bracket 3ay cap plus 4az cap, az cap it is close bracket t, that is the equation given. What is the induced voltage you are supposed to determine? Now already we have evaluated the area of the loop and also the unit normal. in which direction we have evaluated, and of course the vector ds is written in terms of vector entity. Now the flux linkage with the loop, that's phi is equal to integration of vector b dot vector ds. That's a equation you are supposed to use to solve the problem. So actually this is the Faraday law. Normally E is equal to d phi by dt minus d phi by dt, that is the equation. But we have a b here, phi here, we are supposed to take the derivative of it. So before that let us solve what is the value of phi, that's a flux linkage in the loop. So phi is equal to integration of vector b dot vector ds, that can be written as integration of vector b ds into az cap. Here vector b dot az cap is constant throughout the loop. Therefore the phi is written as vector b into az cap integration of ds. That will be constant term taken outside, and dz. You integrate dz. So integration of ds is equal to ds. Okay, that is surface. So when you integrate a small surface, that will give rise to the total surface or surface areas. All right. So S is the total surface area. So you got phi is equal to vector b into az cap into S. Now substitute what is S. S area we are already evaluated. Phi into 0.1 whole square into vector b into az cap. Now b also given, you can just substitute in place of vector b, that is phi is equal to phi into 0.1 whole square into 0.5 cos 377t open bracket ay, 3ay cap plus 4az cap into that az cap unit normal. Now phi is equal to, take the derivative, that is 0.5 into 0.1 square into 0.5 cos 377 t into, I have multiplied this az cap with the 3ay cap plus 4az. Here the dot product of ay dot az, that is 0. So dot product unit vector multiplications I taught you in one of the previous discussion. So ay cap dot az cap is 0, therefore that term is 0. So whereas az cap dot, that's a dot product of another unit vector, that is az cap, that will yields 1, therefore 1 into 4, that will be multiplied to the equations. Therefore phi is equal to, if you simplify, it will be 0.0628 cos of 377t. So once if you get the flux through the loop, or the flux linked to the loop, what is the EMF induced in it? That is E equal to minus d by dt of pi. That's equal to, a constant term is taken outside with the negative sign, d by dt of cos 377t, close bracket. The derivative of cos is minus sign, it will become plus now. So plus 377t into 377. So I multiplied, it will be 23.69 sine of 377t is the EMF induced in the circular loop. That is the answer for the problem. Next numerical. The electric field of a uniform plane wave is given by vector E is equal to 40 sine open bracket 30 pi into 10 power 6t minus 2 pi z close bracket ax cap plus 40 cos open bracket 30 pi into 10 power 6t minus 2 pi z close bracket ay cap volt per meter. Find frequency, wavelength and direction of propagation of wave. Solution for the problem is, in this problem the expression for the E is given. In other words, electric vector is given. E is equal to 40 sine of open bracket 30 pi into 10 power 6 t minus 2 pi z close bracket Ax cap. That's a x component, plus y component is 40 cos of open bracket 30 pi into 10 power 6 t minus 2 pi z close bracket Ay cap. This is the electric vector given. Call this is equation number 1. Now the general equation for a plane wave, then the electric vector of that wave is E equal to E of sine of omega t minus beta z into Ax cap plus cos of omega t minus beta z Ay cap. This equation we have recently used for the discussion of the polarization of a plane wave. Alright, so where E is, in fact it is E naught, that is represents the amplitude of that electromagnetic wave in fact, and the sine theta term and the cos theta term. Now by comparing these expressions we can collect the sum terms. So here the omega is nothing but the angular frequency, beta is the phase constant, and t is the time parameter, z is the direction in which electromagnetic wave is propagating. That is the expression. Now as I said, omega is the angular frequency that can be written as 2 pi f. So one of the unknown parameter is the frequency. From this equation you can evaluate frequency. Free f is equal to omega by 2 pi. So what is omega? That can be evaluated by comparing the equation number 1 and 2. So it is 40 sine, E is equal to 40 and sine omega t, that is 35 into 10 power 60. That means 35 into 10 power 6, that will be the omega term and t term is there. Similarly beta is, it is 2 pi is beta. So that way you can compare and take the beta term as well as the omega term. Let us see how to solve it. As I said, the beta is the phase constant and z is the direction of propagation. So by comparing that, omega equal to 35 into 10 power 6 radian per second, and of course the frequency is 15 megahertz, that is omega by 2 pi, that's 15 megahertz will get, that's a answer for the frequency. Velocity of the wave v is given by f lambda. For an electromagnetic wave traveling in free space, v is equal to 3 into 10 power 8 meter per second. Now the lambda can be evaluated using the velocity of the wave equation, v by f. Therefore lambda is equal to v is 3 into 10 power 8 for an electromagnetic wave divided by frequency, just we have evaluated, it is 15 megahertz, mega means 10 power 6. So if you substitute that, you will get 20 meter is the wavelength. And the last part is the direction of the propagation, the electromagnetic wave. So this can be concluded from the equation itself. In the given equation, z is the coefficient of beta. So that will represent the direction of propagation of the wave. Therefore, z is the direction of propagation of the given wave. So with this topic I will stop here. Thank you.